B0 field inhomogeneities can lead to a very chemical shift. The water suppression RF pulse will mismatch with the water peak, which leads to the bad water suppression. This is how we do the shimming at our institute. Click the option Adjustment, Adjust On, and wait until on criteria turn green. In the manual adjustment window, select the interactive shim tab and start shimming by clicking Measure. We will monitor the result up FWHM and T2 star. We can repeat by plus or minus the step for XYZ channels until you are satisfied with the result. Applying the shimming result to the next spectrum measurements. When changing the shimming, the frequency will be adjusted, and if it's not done manually, the system will handle it automatically. The last part of my presentation is post-processing. There are some useful third-party post-processing software, and in this my presentation, I would like to mention the post-processing in Siemens Singovia. To see the pickup not show in the scanner, we can add a pick. And for this example, we can add the lactate. Some peaks in the spectrum are very small, so to better show these peaks, zoom in on them and change the scale of y-axis. The reference spectrum curve mean the red line and the default peak information are overlaid, and this display can be customized by hiding the reference spectrum. Next is metabolic map. Metabolic map represent the voxel-dependent intensity ratios of different metabolites within a void. For example, the choline and lactate ratio. Click on the CSI parameters to customize the display of the metabolic map. And we can click on the movie to display metabolite concentrations in different metrics. We can remove the setband, the voxel squares to see the map more clearly. And for this example, the choline is highest at this position. It's possible to display a map of one metabolite only, for example, the lactate. We can obtain the location of the highest lactate concentration here and compare with the corresponding voxel location to compare with the spectrum images. This is a sample show the choline map localized to disease area. Select user define, press Ctrl and left mouse to draw the ROI by yourself. The result only draw areas shows the map on image. We can clicking on the peak info map will display the specific peak values of metabolite ratios. Besides the metabolic map, we can create the spectral map from CSI. And finally, the result was displayed in the data box like this. This is some references, and that's all for my presentation. Thank you for your attention.
Thank you very much, Naman, for your excellent and amazing talk. Very, very informative. All three talks have been absolutely amazing. We are grateful for you all for making this Emerging Regions Initiative hosting for Vietnam a great success. So we're going to move on to the questions, please. So some people, we can see some questions popping through. So if anyone has questions, all three speakers are online now to answer your questions. So for the first one for Dr. Tao, we've got a question in which states, in your institution, what is the number of axes with diffusion tensor imaging in usual? So what is the normal number of axes? And do you change it in each disease?
Okay, hi. Thank you very much. So for the first question, it's a very good question. It depends on the study you are doing. So typically we do 64 directions, but the more direction you do, the longer the sequence are. So in practice, normally we do 30 direction for clinical patient, but for some research we will keep with 64 direction.
Okay, great. Thank you very much for that. Please keep on posting your questions. And we have one question from Gary Detzler who says, could you please clarify why the voxel should be placed on an axial image?
Okay, thank you for your question. Please wait some seconds. Okay, can you see my slide?
Yes, we can see the slide.
Sometimes we have some mistake when doing the CSI processing. So I think the best way to best way to limit that mistake is we have to plan the MRS and localizer strict in axial plane because we have the nearest operation. So if we do exactly on axial plane, the other two planes will be correct due to the nearest right here.
Right, okay. Great, thank you for explaining that. If anyone does have any more questions, please keep on posting them in the chat box so we can see them. So the next question is from Hero to Dr. Tan, and he's asking, is it automatic to create a tractography with DTI? Is it done by the person? And can they already be fully automated with deep learning, etc.?
Yeah, thank you, Hirozuki, for the very, very excellent question. Actually, we have like a manual tractography, we have semi-automatic tractography, or we have automatic tractography. But in the clinical setting, I think the manual tractography will be like a time consuming. So I hate to do that. So normally I will perform some automatic pipeline process to perform the tractography by using some third-party software. Like I have to mention a most citation software now is FSL and DSI Studio. So I think you can take a look about the website of the both of the sequence, the the software to do the automatic tractography.
Okay, thank you. V, would you like to ask a couple of questions in the chat?
Yes. James have question for Dr. Thao. So as the machine learning technique become more sophisticated, how might AI-powered approach to DTI and data analysis, such as automate fiber tracking or predictive modeling of neurodegenerative disease, transform the clinical utility of this neuroimaging tool?
Yeah, that's a great question. That actually the AI is become day by day very useful and practical now, and in the near future we might have the AI power approach to the DTI, and it can help us in many several ways. For example, it can help us to automatically fiber tracking. So the current approach that we do it manually or semi-automatic, and it's very time consuming and very doctor dependent and technically dependent. So with the help of AI, we can do it automatically with more precision and quicker. The second thing is we can use AI to integrate the DTI with other model like the functional MRI. So it can help us to better better can diagnose disease more earlier before the become symptomatically. And the third thing is that with AI we can use to analyze the large scale data. So we can use the big data to analyze with a large number of patients, and it may help also to real-time analysis. Currently, it takes many time for the data acquisition and also post-processing. With the help of AI in the future, it can help us to have it real time. Yes, so many potential application of the AI in the field.
Okay, thank you very much, Tao. We've got a few more questions. I'm just going to address Heroes first. He's asking, have you ever used quantitative MRS software such as LC model for brain disorders? If so, what is the situation for?
I think there's a question for Chan. Can you
Yes.
for now on? Okay. Can you answer it?
Yeah, thank you for your question. I still never get the chance to use LC model, but I'm used to use the used to JMR UI to assess the disease. Multiple studies have done some common application include that sometimes some kind of Alzheimer disease. So JMRUI, I can use it to analyze MRS data and identify change in metabolite levels associated with the Alzheimer disease, such as the levels of the exact level criteria of NAA and increase the levels of choline containing compounds choline. The second disease is multiple sclerosis, MS. I use it to assess the change in brain lesions and normal appearing white matter in using in MS patients and potentially adding in the disease monitoring and treatment evaluation. Some neurodegenerative disease like Huntington disease or Parkinson disease, I can use JMRUI to quantify the exact integrals of metabolite.
Thank you, Nam An. And there is another question. So in what in what way can simultaneously acquiring structure MRI, fMRI, and MRS data enable multimodal model to better characterize the relationship between brain structure, function, and neurochemistry in both healthy and disease state.
Yeah, it's a very tricky question that we cannot acquire the data simultaneously, but one by one. So